So this is Chapter 4, Part 1, Pre-Class Lecture, starting with Section 4.2 of the Chapter 4, Part 1 notes. And so, in class on Monday, we talked about different ionic compounds, both how to name them, as well as how to write the formulas for our ionic compounds. And one of the types of carbon sources that we focused on that's a part of the carbon cycle, carbonate being one of the many polyatomic ions that are often found in ionic compounds. And so in focusing on the carbon cycle and therefore carbon, we can have a discussion on where on the Earth, which includes the Earth's surface, as well as the Earth's atmosphere, can you find carbon atoms? And you find carbon atoms as part of compounds and not as single carbon atoms. And so carbon atoms are a part of compounds in different parts of the Earth, which we call reservoirs. So in the atmosphere, you find carbon in various molecules. The most dominant one being carbon dioxide, CO2. Also in the atmosphere, there's carbon monoxide, CO, and methane, CH4. In the Earth's crust, you'll find carbon in the form of carbonate, which is a polyatomic ion with the formula CO3 2-. And you find carbonate in the form of ionic compounds in minerals that are deposited in rocks. And then you'll also find carbon on the Earth's surface in plants as well as animals. And so in plants as well as animals, you'll find different molecules that contain carbon, such as carbohydrates, lipids, and I put carbohydrates twice when I meant to put, in addition to carbohydrates and lipids, proteins. All three of these biological molecules, they're also called macromolecules because they're very large. Carbohydrates, lipids, and proteins, they're found in both plants and animals. Lipids, of course, are also called fats. And so we've talked about three different reservoirs where carbon atoms are found: the atmosphere, in the Earth's crust in the form of minerals that reside in rocks, and then in the macromolecules that make up plants and animals. And then we can add a fourth reservoir to this list: the Earth's surface waters, oceans. In the Earth's surface waters and oceans, you'll find carbon mainly in the form of carbon dioxide dissolved in that surface water. And so the carbon atoms that are a part of these molecules, some of them stay stationary in their particular reservoir, but many of them do not. So many of them are on the move. And so in the picture shown here, which is a picture of the carbon cycle, the red arrows that you see in this figure show the movement of carbon. So wherever you see red arrows, those red arrows are representing movement of carbon atoms, in particular molecules. And so we first can look at the atmosphere. And the atmosphere, having about 750 GT. This GT stands for gigaton. And so gigaton is a unit of mass. 1 gigaton is equivalent to 1 times 10 to the 12 kilograms, which is also equal to 1 times 10 to the 15th grams. So in taking a look at some of these red arrows, we see that plants, which undergo photosynthesis reactions, so that's one of the red arrows representing movement of carbon atoms. And its photosynthesis and respiration go hand in hand. They are like the opposite of each other. And therefore they balance each other. And so respiration is when oxygen and glucose combine, and the products are carbon dioxide and water. And so non-photosynthetic organisms perform this respiration reaction. So non-photosynthetic organisms like humans or farm animals and so on and so forth. So we breathe in oxygen, and therefore we're able to take the glucose in the foods that we eat and convert it into energy. And then, of course, 2 other products are carbon dioxide and water. And so in breathing out the carbon dioxide, photosynthetic organisms undergo photosynthesis reactions, and they take in the CO2 and water and produce oxygen and glucose. And so those 2 processes of moving carbon dioxide, those 2 processes balance each other out. So respiration puts carbon dioxide in the atmosphere at a rate of 60 gigatons per year. And then photosynthesis balances that by removing CO2 from the atmosphere at a rate of 61 gigatons per year. So those 2 processes balance each other out pretty closely. And then you have the exchange of CO2 between the atmosphere and the ocean. And so CO2 moves from the atmosphere to the surface waters and oceans at a rate of about 92 gigatons per year. And then that CO2 is dissolved in the surface water. And through evaporation, the CO2 moves from the surface waters and oceans back up into the atmosphere at a rate of about 90 gigatons per year. So those two processes pretty much balance each other out as well. So that's called the ocean to atmosphere CO2 exchange. And so whenever you have CO2, which is a gas, or a solid for that matter, when they dissolve in a liquid like the ocean water, that solid or that gas that gets dissolved in the liquid, they're called solutes. The liquid dissolving the solid or gas is called the solvent. The solute and the solvent combined together form a homogeneous mixture, also called a solution. And so when it rains and snows, which we call precipitation, and so when the solid solute that's dissolved in the water, if excess amount of solid is added to a given volume of water, then the solid will start to fall out of solution, because the solution is then called supersaturated. It has too much solid solute in it, more than that particular volume of liquid can handle. And so the solid that falls out of solution is called a precipitate. And so we learned in lab that combining certain ionic compound solutions together can form a solid precipitate product. And that solid precipitate product will fall out of solution and therefore separate itself from the other product, which is an aqueous solution. And if you dissolve a gas like carbon dioxide in water, a solvent, a liquid solvent, and if you add too much gas, it again becomes supersaturated, and a process called degasification occurs, meaning that the gas solute falls out of solution. And therefore, you'll have that gas separating itself from the liquid solution. And so the ocean to atmosphere CO2 gas exchange are two processes that are balanced. The dissolving of CO2 in the ocean water, and then that CO2 evaporating, coming out of solution, and going back up into the atmosphere. Those two processes are balanced. And so you also note that there are some other arrows that we haven't talked about. You've got deforestation. You've got reforestation. And then you've also got burning fossil fuel. So burning fossil fuel adds 6 gigatons per year of CO2 into the atmosphere. The cutting down of trees, and of course we know trees are photosynthetic organisms, they remove CO2 from the atmosphere. So if there are less trees on the planet, less CO2 is being taken out of the atmosphere. And so you're unbalancing the photosynthesis and respiration processes. So deforestation adds 1.5 gigatons per year of CO2. And then the burning of fossil fuels add another 6 gigatons per year. And so by these processes not being balanced, the deforestation, reforestation, growing more trees takes out a half a gigaton a year. But the deforestation is putting up 1.5 gigatons per year. So that's not balanced. And then in addition to that, 1 gigaton unbalance between deforestation and reforestation, the burning of fossil fuels adds another 6 gigatons per year. And so that being overall, having these deforestation and burning of fossil fuels unbalanced processes, that those processes therefore adding excess CO2 into the atmosphere. And so that's kind of a way of upsetting the balance of the carbon cycle. So your unbalanced mechanisms being the burning of fossil fuels and deforestation. And so the things that we do and that we need to use in our everyday lives that are very, very important because they are sources of CO2 emissions. And these are all, of course, human activities. And so things such as transportation, deforestation, industry, power and heating stations and agriculture, and also waste and wastewater. All of those things and those various percentages are sources of adding excess CO2 into the atmosphere. And so burning fossil fuels and deforestation combined puts an additional 7.5 gigatons of carbon in the atmosphere. A little over half of this gets absorbed by the oceans. So therefore, about 3.1 to 3.5 net gigatons of the carbon that's put into the atmosphere due to deforestation and burning fossil fuels actually remains in the atmosphere. There's not any counterbalancing processes that is removing that 3.1 to 3.5 gigatons of CO2. And so the carbon in the form of CO2, that 3.1 to 3.5 gigatons, stays in the atmosphere. And so if you have 3.3 gigatons of carbon that's remaining in the atmosphere, that's right there smack in the middle of the 3.1 to 3.5 range. And if the source of this carbon is CO2, then what mass of CO2 contains 3.3 gigatons of carbon? So we will answer that question shortly. And so in thinking about carbon, quantifying carbon, we will first quantify carbon based on mass. And mass, we can use several different units: gram, kilogram, and then this new unit that we just introduced, gigaton. And so carbon is, of course, an element on the periodic table. And we can take a look at the periodic table, and we see that carbon has an atomic mass of 12.011. And of course, the units are gram per mole. Another unit that you can use for atomic mass is called the AMU. AMU stands for atomic mass unit. One atomic mass unit is the same thing as 1 gram per mole. So you can use the atomic mass unit and the gram per mole interchangeably because they mean absolutely the same thing. So 12.011 AMUs or 12.011 grams per mole is the atomic mass of carbon. And so that atomic mass on the periodic table is actually the weighted average of all of the naturally occurring isotopes that exist in the Earth for that particular element. Isotopes are the same element, but they're different versions of that element. Isotopes have equal numbers of protons because they're the same element. But what makes isotopes of the same element different from each other is that they have a different amount of neutrons. And so we learned earlier that the mass number is equal to the number of protons plus the number of neutrons. And so therefore, different isotopes of the same element will have different numbers of neutrons and therefore different mass numbers, but they will have the same number of protons. So carbon has 3 main isotopes: carbon-12, carbon-13, and carbon-14. And so those representations, 12, 13, and 14, represents the mass numbers of each of these 3 isotopes of carbon. And so carbon-12 is the most abundant isotope of carbon. 98.90% of all carbon in the Earth is in the form of carbon-12. Another 1.10% of all carbon in the Earth is carbon-13, and then approximately 0.001% of all carbon in the Earth is carbon-14. So therefore, each one of these isotopes contributes to that atomic mass of 12.011 grams per mole that we see on the periodic table. Carbon-12 contributes 11.868 grams per mole of the total 12.011. And then carbon-13 is 0.143 grams per mole of the total atomic mass. And then carbon-14 is only 0.0001 grams per mole of the total atomic mass. If you add these 3 numbers together, you'll get 12.011. And so you may say, well, how did we get these numbers? And so the mass number for carbon-12 is 12, and it is 98.90% of all carbon that exists in the Earth's crust. So we change that percent to a decimal, multiply that decimal by 12, you'll get 11.868. And so same thing with 0.143. That number was obtained by taking the mass number for carbon-13, 13, changing the percent, 1.10, to a decimal, and multiplying that decimal by 13, you'll get 0.143. And then the same thing for carbon-14, take its mass number, multiply it by the decimal. So you need to convert the percent to a decimal. And you just move the decimal 2 spaces to the left to convert the percent to a decimal. Multiply that decimal by 14, you get 0.0001. And so therefore, adding these 3 numbers together, you'll get 12.011. So that's how the atomic mass that you see on the periodic table, that's how it's calculated. But you have to know what relative percent abundance that each isotope is present in the in the Earth. So what percentage of all carbon, for example, is carbon-12? What percentage is carbon-13? What percentage is carbon-14? And then you take those percentages, convert them to decimals, and then multiply each decimal by its mass number. And so taking a look at this data table, we have in the first two rows two isotopes of nitrogen, nitrogen-14 and nitrogen-15. So their mass numbers are 14 and 15, respectively. And so therefore nitrogen, if we look it up on the periodic table, it is atomic number 7. So therefore nitrogen has 7 protons. And therefore, by being a neutral atom, nitrogen will also have 7 electrons. So now the number of neutrons is calculated by taking the mass number and subtracting the number of protons from the mass number. So nitrogen-14 has 14 minus 7 neutrons, 14 minus 7 being equal to 7. However, nitrogen-15 has 8 neutrons, 15 minus 7. The next two isotopes are isotopes of oxygen, oxygen-16 and oxygen-18. Oxygen is atomic number 8. So oxygen has 8 protons. So oxygen-16 and oxygen-18, they're both oxygen. They're the same atomic number, 8. So they both have 8 protons. And they will also have 8 electrons, because for neutral atoms, they have the same number of electrons as protons. Then the number of neutrons can be calculated again by subtracting the number of protons from the mass number. So oxygen-16 has 8 neutrons. Oxygen-18 has 10 neutrons. And then finally, we have an isotope of phosphorus, phosphorus-31. Phosphorus is atomic number 15, so it has 15 protons. Phosphorus-31, mass number being 31, 15 protons and 15 electrons, and subtracting 15 from 31, you get 16. So it has 16 neutrons. So in the next example, we have two isotopes of silver. Silver has the symbol capital A, lowercase g. So silver 107, it has an atomic mass of 106.91 grams per mole. So silver 107, mass number is 107. And of all the silver in the earth, silver 107 makes up 51.8% of all of the natural silver that's in the earth. And then the second isotope, silver 109, with atomic mass 108.91 grams per mole, it accounts for the other 48.2% of all silver that exists in the Earth's crust. What is the average atomic mass of silver? So the average atomic mass is going to be equal to the mass number times the fractional or decimal abundance. For isotope 1, plus the mass number times the fractional abundance for isotope number 2. So on and so forth. Because you can have several different isotopes. Some elements like silver only have 2 isotopes. Others, for example, like carbon, has 3. There are other elements that may have 4 or 5 different isotopes. So you follow this same formula. You take the mass number, multiply it by its fractional abundance. How do you get the fractional abundance? You just take the percent and convert it into a decimal. And then you add to that the same for isotope number 2. It's mass number times its fractional abundance plus isotope number 3. If there's not a third isotope, it's mass number times the fractional abundance for that isotope, so on and so forth. So for silver, we only have 2 isotopes. So to get the average atomic mass for silver, we take the mass number for the first isotope, which is 107, times its fractional abundance. We take 51.8, convert it to a decimal. Add to that the mass number for isotope number 2, which is 109. Multiply it by its fractional abundance, 48.2%, convert it to a decimal. We do the math, and we get 107. And we're going to have 3 decimal places in our answer because we're adding. And our significant figure rule says that when we're adding or subtracting, we need to add the proper number of decimal places. And so 107 and 109 are exact numbers, whereas those fractional abundance are measured values. And so we want to follow the number of decimal places as the measured values have and the fewer number of decimal places. Each of these measured values have 3 decimal places. So we want to have 3 decimal places in our answer. So we have 107.964 grams per mole. And if we take a look at this periodic table, find silver, and we see that we get very close to what is listed on the periodic table for the atomic mass of silver. And so we've talked about mass in quantifying carbon. And mass can be in grams or kilograms or gigatons. The next way we can quantify carbon, once we know the mass, is moles and also molecules and atoms. Carbon itself is an element. So we can refer to carbon in terms of mass, like grams or kilograms or gigatons, or we can classify carbon in terms of moles. And then we can also refer to carbon in terms of atoms, because carbon is an element, so therefore we can talk about it on the atomic level. However, if carbon is a part of a molecule or compound like carbon dioxide, then we can refer to carbon dioxide in terms of molecules. And so therefore, to convert between grams and moles, we need to know a conversion factor called the molar mass. If we are dealing with a molecule or a compound. For atoms, if we want to convert between grams and moles of an atom, then we need to use the atomic mass that we find on the periodic table. And we can use that too as a conversion factor to convert between grams and moles of an atom. But if we want to convert between grams and moles of a molecule or compound, then we need to know the molar mass of that compound or molecule. and use it as a conversion factor to convert between mass in grams and moles. So the molar mass of a compound is the sum of the atomic masses of all of the atoms in the formula of that compound. The units for molar mass are grams per mole. A mole is defined as the number of carbon atoms in exactly 12 grams of pure carbon-12. And so 1 mole is equivalent to 6.022 times 10 to the 23rd entities. And that entity can be an atom or molecule or ion. So 1 mole of carbon atoms, 1 mole of carbon is equivalent to 6.022 times 10 to the 23rd atoms of carbon. 1 mole of carbon dioxide, CO2, is equal to 6.022 times 10 to the 23rd molecules of CO2. And so in most periodic tables, you'll see the element symbol. The atomic number will usually appear above the symbol for the element. And then that is a mistake there. That is not the mass number. That is the atomic mass that you'll normally find beneath the symbol of the element on the periodic table. So Avogadro's number, 1 mole being equal to 6.022 times 10 to the 23rd entities, Avogadro's number is also a conversion factor that you can use to convert between moles and entities. And the entity can either be an atom or a molecule or an ion for that matter. So Avogadro's number is equal to 6.022 times 10 to the 23rd atoms or molecules per mole of an element or a compound. So therefore, if you want to interconvert between grams and moles of a compound, use the molar mass of that compound. If you want to convert between moles of that compound and atoms or molecules, then use Avogadro's number. So if you're interconverting between grams and moles of an element, you'll use the atomic mass. But if you're interconverting between grams and moles of a compound, then you'll use the molar mass of that compound. And then to interconvert between moles and entities, which can either be an atom if you're dealing with an element or a molecule if you're dealing with a compound, use Avogadro's number. So taking a look at a couple of examples. And so in recapping our 2 conversion factors, the molar mass, or if we're dealing with an element, the atomic mass. So if we have mass of an element, we can convert the mass of an element in grams to moles of an element by dividing by the atomic mass. And then we can go in the opposite direction. If we know the number of moles of an element, we can convert the moles to mass in grams by multiplying by the atomic mass. And then we can convert moles of an element to atoms of an element by multiplying by Avogadro's number. Avogadro's number is often abbreviated in textbooks with a capital N and a capital A subscript. And then you can go in the opposite direction, convert atoms of an element to moles of an element by dividing by Avogadro's number. Then you can do these same calculations for a compound. So if you have the mass of a compound in grams, you can convert that mass to moles by dividing by the molar mass for that compound. And again, you can go in the opposite direction, converting moles of a compound to mass of a compound in grams by multiplying by the molar mass. And then you can convert moles of a compound to molecules by multiplying by Avogadro's number. And then you can go in the opposite direction. So those are helpful flowcharts to keep handy when you're doing calculations that require you to convert between grams and moles, between moles and atoms, or between moles and molecules. So if we have 36 grams of carbon, how many atoms of carbon do we have? And remember, Avogadro's number is 6.022 times 10 to the 23rd entities per mole. And the entity can either be an atom or a molecule, depending on whether you're dealing with an element or a compound. So in this example, we're dealing with carbon, which is an element. So we want to know how many atoms of carbon do we have in 36 grams of carbon. So we're here at grams. So we need to convert the grams first to moles and then convert the moles to atoms. So we have a two-step calculation to do. We first have to use the atomic mass of carbon as a conversion factor and convert it to moles of carbon by dividing by the atomic mass of carbon. So we're here on the flow chart. We know mass. We're going to first convert the mass to moles by dividing by the atomic mass of carbon, which is 12.011 grams of carbon per mole of carbon. The grams of carbon cancel. And the second step, we're going to take the moles of carbon and convert to atoms of carbon by multiplying by Avogadro's number. And our entity is atoms per mole. So now moles of carbon cancel. So now we're ready to do the math. 36.0 times 6.022 times 10 to the 23rd. And then we'll take that result and divide by 12.011. And we get 1 point. And we need 3 significant figures in our answer. So 1.80 times 10 to the 24th atoms of carbon. The next example, if we have 8.9 times 10 to the 24th atoms of carbon, how many grams of carbon do we have? So now we're going to be starting with atoms and working our way backwards. So first we're going to convert the atoms to moles by dividing by Avogadro's number, and then converting the moles to mass in grams by multiplying by the atomic mass of carbon. So again, we have a two-step calculation. We're going to take the 8.9 times 10 to the 24th atoms of carbon, and we're going to divide by Avogadro's number. Atoms of carbon per mole of carbon. So now the atoms of carbon cancel. And then the second step, convert the moles of carbon to mass in grams of carbon by multiplying by the atomic mass of carbon. The moles of carbon cancel. So now we do the math. 8.9 times 10 to the 24 times 12.011. Get that result and divide by Avogadro's number, 6.022 times 10 to the 23rd. And we get 100, 1.8 times 10 to the second grams of carbon. And so when we burn coal, coal is mostly carbon. And in the United States, we get over 80% of all of our electricity from burning coal. So when coal combusts, it reacts with oxygen and it gives off heat, of course. But one of the products also is carbon dioxide, CO2. And so this is a balanced reaction. All stoichiometric coefficients in front of each reactant and the product, CO2, are ones. So what that's saying is for every 1 mole of carbon that's combusted, you produce 1 mole of carbon dioxide, CO2. So therefore, if we have 100 grams of CO2, how many grams of carbon are in this 100 grams of CO2? And so now we can build on our flow chart. So if we know how many grams of reactant that we have, we can convert grams of reactant into moles of reactant by dividing by the molar mass or atomic mass. And then we can go in the opposite direction by multiplying by the molar mass or atomic mass if we're dealing with an element. And then we can convert the moles of reactant into moles of product. By multiplying by the mole ratio. Moles of product divided by moles of reactant. And that's called a mole ratio from the balanced equation. And our reactant is carbon. For every 1 mole of carbon, you produce 1 mole of CO2. And then, of course, you can go in the opposite direction by multiplying by the reciprocal. Moles of moles of reactant divided by moles of product will allow you to convert the moles of product into moles of reactant, going in the opposite direction. And then once you know moles of product, you can convert moles of product to grams of product. By multiplying by the molar mass for the products. And then, of course, going in the opposite direction, you divide by the molar mass. So this is an updated flow chart that will enable us to solve the question, how many grams of carbon are in 100 grams of CO2? So if we have 100 grams of CO2, we can convert the grams of CO2, which is our product. So we are at grams of product. CO2 is a product. We're going to go backwards and convert grams of CO2 into moles of CO2 by dividing by the molar mass of CO2, which is 44.011 grams per mole. So now grams of CO2 cancel. And then now that we've got moles of product, we're going to now convert the moles of product into moles of reactant, carbon, by multiplying by this ratio, moles of reactant divided by moles of product from the balanced chemical reaction. And there's 1 mole of carbon for every 1 mole of CO2. So now moles of CO2 cancel. And then the last step, we'll convert moles of carbon to grams of carbon by multiplying by the atomic mass for carbon. And now moles of carbon cancel. and you're left with the unit that you want, grams of carbon. So now just do the math. 100 times 1 times 12.011. Get that result and divide by 44.01, and you get 27.3 grams of carbon. So now we're ready to answer that previous question. If we're netting 3.3 gigatons of carbon being added to the atmosphere by the burning of fossil fuels and deforestation, and if 1 gigaton is 1 times 10 to the 15 grams, what mass of CO2 contains 3.3 gigatons of carbon? So if we have 3.3 gigatons of carbon, how many gigatons of CO2 is this? And so therefore, the atomic mass of carbon being 12.011, and so instead of using grams per mole, we can use gigatons per mole. And then our mole ratio from our balanced equation, there's 1 mole of carbon for every 1 mole of CO2 that reacts. So gigatons of carbon have canceled, moles of carbon have canceled. So now we're going to convert moles of CO2 to grams of CO2 by using the molar mass of CO2, 44.011 grams of CO2 per mole of CO2. So now moles of CO2 cancel. So now we just do our math, and we get 12.1 gigatons of CO2. Now we can convert this 12.1 gigatons of CO2 into grams of CO2. One gigaton is 1 times 10 to the 15th grams. So that comes up to be 1.21 times 10 to the 16th grams of CO2. So we can give our mass answer in gigatons, or we can give our answer in grams. So the next part of the notes is just a review of what we talked about earlier in the semester, the first week or two of the semester, significant figures. So that's the same review that's in the math review packet that we looked at the first week and second week of class. And so you can just review those rules and notes on significant figures. And so in calculating the molar mass for a compound, you take the formula of the compound and you look up the atomic mass for each element that's in the formula of the compound. For ozone, it only has oxygen atoms. It has 3 of them. And each oxygen atom has an atomic mass of 16 grams per mole, giving ozone an atomic mass of 48 grams per mole. N2O is a secondary air pollutant. It's composed of nitrogen and oxygen. There are 2 nitrogens, each having an atomic mass of 14.007 grams per mole. So a combined atomic mass of 28.14 grams per mole. And there's just 1 oxygen, 16 grams per mole. Add those together, you get 44.14 grams per mole. And then CCl3F, this is Freon 11. It has one carbon atom. Carbon has an atomic mass of 12.011. There are 3 chlorines in the formula. Each chlorine has an atomic mass of 35.45 grams per mole. Do the math. And then finally, fluorine, there's 1 in the formula. Each fluorine is 18.998 grams per mole. So add those 3 numbers together, you get 137.359 grams per mole for the molar mass of Freon 11. And this next problem we've already done previously, calculating the atomic mass for silver. Question 3, if we have 5.00 times 10 to the 45th silver atoms, what is that mass in grams? Silver symbol is Ag. So we'll go from atoms to moles, and then moles to grams. So we'll go from atoms, using Avogadro's number, dividing by Avogadro's number, converting the grams to moles, and then converting the moles to grams by multiplying by the atomic mass for silver. So first we'll divide by Avogadro's number. So atoms of silver cancel. And then we'll multiply by the atomic mass for silver. So the atomic mass of silver is 107.87 grams per mole. And so moles of silver cancel. You get 8.96 times 10 to the 23rd grams of silver. And so going back to number 2, calculate the average mass in grams of an individual atom of silver. Well, we know what the average, what the atomic mass of silver is. And so the average mass, taking that atomic mass and since we've already figured this part out from the previous question, we needed to do one more step and take that atomic mass that we've already calculated, divide by Avogadro's number, and we'll get how many grams per atom. So in doing the math, we get 1.791 times 10 to the negative 22 grams per atom. And then question 4, the mass percent of chlorine in CCl3F, which is Freon 11. Well, we've already calculated the atomic mass of the molar mass of Freon 11, 137.359. And then there are 3 chlorines in Freon 11. So the mass percent chlorine is going to be equal to the total atomic mass of all 3 chlorines divided by the molar mass of Freon 11. And so the total atomic mass of the chlorines there are 3 of them, and each has an atomic mass of 35.45 grams per mole. You're going to divide that by the molar mass of Freon 11, 137.359 grams per mole, and then multiply by 100. The grams per mole units cancel. So 3 times 35.45, get that result, and then divide by 137.359, and you get 77.43%. So 77.43% of Freon 11 is chlorine. That's why Freon 11 was so bad for the ozone layer, because for every molecule of Freon 11 that was being put in the atmosphere, 3 chlorine radicals can form. And therefore, you've got 3 chlorine radicals free to break down ozone per every molecule of Freon 11 that we put into the atmosphere. So that's why it was so bad for the ozone layer. Number 5, what is the maximum mass of chlorine that could be released in the stratosphere, in the ozone layer of the stratosphere, by 100 grams of CCl4? So if we have 100 grams of CCl3F, which is Freon 11, and for every molecule of Freon 11, if 77.43% of it is chlorine, then take that percent, convert it to a decimal, multiply it by the total mass of Freon 11 that we have in this question, which is 100 grams, and you get 77.43 grams of chlorine. And then what's the maximum number of chlorine atoms that could be released in the stratosphere by 100 grams of Freon 11? So if 100 grams of Freon 11 contains 77.43 grams of chlorine, we can convert the grams of chlorine to moles of chlorine by dividing by the atomic mass of chlorine, and then multiply by Avogadro's number to convert the moles of chlorine to atoms of chlorine. The grams of chlorine cancel, the moles of chlorine cancel. We do our math, 77.43 times Avogadro's number, and then divide by 35.45. You get 1.315 times 10 to the 24 atoms of chlorine. So what we did, we took grams of chlorine, 77.43. We convert it to moles by dividing by the atomic mass of chlorine. And then we convert the moles of chlorine to atoms of chlorine by multiplying by Avogadro's number. And that brings us to the end of part 1, chapter 4, pre-class lecture.